Hello there! In this lesson we're going to learn about periodic table trends. So you already know that the periodic table was put together to organize atoms according to their atomic mass originally, and now it's atomic number, the number of protons. And so what happens is that you end up getting patterns of similar properties periodically. So that's why it repeats, like as you go, 1, 2, 3, 4, etc. They found that element 1 acted like element 3, which acted like the next element down here, which I think is 11, and so forth. And so that's why they called it the periodic table. Now, once it's arranged this way, there are a bunch of other patterns that also emerge, and so that's what we're going to look at today. Some of these patterns are going to include radius, ionization energy, electron affinity, electronegativity, and reactivity. So they're all related to the position on the periodic table and the properties that the atoms have in a given column or row. So as a reminder, let's look over what the columns and rows are called. On your periodic table in the classroom, you might see the word group. And so group refers to the columns. So this is group 1 here. And group 2, you can see the column there. So it goes down like that. And then 3, 4, etc. 13, 14 over here, all the way up to 18. So those are your groups. And then down the side here, you see the word period. And so it's period 1, 2, 3. And those are the rows that go from left to right. So when we're going to look at these periodic table trends, we're going to talk about what is the trend for a group and what is the trend for a period, and we'll try to make sense of why different elements behave the way they do. So the main explanation we're going to use for all of these properties can be related to what's called Coulombs Law. So Coulombs Law is the mathematical relationship between the attraction or repulsion between charged objects and the amount of charge, fancy word for amount is magnitude, and the distance between the two charged objects or particles. And so in this case, what we're talking about is the nucleus for one of the objects, right? Because the nucleus has that positive charge, and then the electrons, which have the negative charge. So it's going to be attraction that we are looking at here that's going to hold an atom together or hold the electrons to the nucleus. And so there's a relationship between the amount of charge, especially in the nucleus, and the attraction to the electrons, as well as the distance. And you can see the distance is squared there, so the distance has a bigger effect than the size of the charge. And so distance is going to be affected by like how many layers of electrons there are around the nucleus. If you're an electron way out here in the outer layer, you're not going to feel as much attraction as one that's in the inner layer. And also the amount of charge that's in here. So if you have 3 protons in the nucleus, there won't be as much attraction as if you had 15 electrons in the nucleus. So we're going to look at both the charge differences and the distance, basically the number of protons in the nucleus and the number of layers of electrons. And so Bohr-Rutherford diagrams are suitable for this. You don't need to worry about quantum theory to be able to understand what's going on when it comes to the periodic table trends. Okay, the first trend we're going to look at here is that of atomic radius, radius being the distance between the nucleus and the valence shell of electrons. So with lithium, there are 2 shells of electrons, and then as you go down this group, you can see that on each subsequent step down the group, you get another layer of electrons. And so as you add layers of electrons, well, of course, the radius is going to increase. And by the time you get down to francium, there are 7 layers of electrons. And so francium's a really big atom compared to lithium because you add so many layers of electrons. Now going across a period, you see that the radius decreases. So we are still adding electrons, only they're going into the same layer. And the result is that the atom is going to be smaller because of that. So what is it that we could use to explain why we have a smaller atom as we're going across a period on the periodic table? Well, it comes back to that Coulombs Law explanation. If you look at lithium here, lithium has 3 protons in the nucleus, and it's got, that 1 electron out in its valence shell. And by the time you get to neon, you've got an atom with 10 protons in the nucleus. Same number of shells, only like that's a lot bigger. You can think of it like a magnet. It's a lot bigger magnet in the center there, a lot bigger charge in the nucleus. And so those 8 valence electrons that are all spread out around the valence shell of neon are going to be held a lot more tightly to that nucleus because of the extra protons that are in there. Remember, most of the atom is empty space, and so there's lots of space for it to compress inwards as those electrons are attracted to the nucleus. So there you go, 2 trends. As you go down, shells are added, and so the radius gets bigger. As you go across, more protons are added, and so the radius gets smaller. Ions form in 2 different ways, as you know. Some ions form as electrons are added, and others formed when electrons are taken away. Now, when electrons are added, what you're doing is you're not changing anything else about the atom except those valence electrons, and you added another valence electron into that shell. And so those electrons kind of repel each other a little bit, and so a negatively charged ion will be a little bit bigger, expand out a little wee bit more than its neutral parent, because that extra electron is going to repel the other electrons in that radius or in that valence shell a little bit further from the nucleus. With a positively charged ion, it's always going to be quite a bit smaller than the parent. Remember, lithium here has an inner shell here with 2 electrons and then an outer shell with just the 1. And then to make a lithium ion, you're going to get rid of that 1 valence shell electron, and then that means this inner layer becomes the valence shell, and it's a whole lot smaller. So much smaller when you get to the ion that has lost that outer layer. Alrighty, let's use what we've learned so far to make some predictions about the radius of these ions and atoms that we have below here. So for the first group, we've got phosphorus, which is here, and we've got magnesium, which is here, we've got chlorine, which is here, and we've got aluminum, which is here. And it says to arrange these in order of increasing radius. So of these, which one will be the largest? It'll be the magnesium, because it has the fewest protons in the nucleus, and therefore the least attraction to its valence shell. And then you can go work backwards from there. You got aluminum, which would be the second smallest nucleus, and then you've got phosphorus, and then you got chlorine. So chlorine would be the smallest one here, and magnesium would be the biggest. All right, for ions, I find it's a good idea to make a little chart to keep track of what we have here, because there can be some similarities that make it difficult to make the call. So I like making a little chart to show the number of protons and electrons that we're dealing with, and then we can make the call as to which one will be bigger and smaller. Okay, so for protons, we know that calcium has 20. We just like use the atomic number there. Sulfur has 16. Sodium has 11, and fluorine has 9. And then let's see the number of electrons. So calcium's going to lose 2 and have 18. Sulfur is going to gain 2 and have 18. Sodium is going to lose 1 and have 10. Fluorine's going to lose 1 or gain 1 and also have 10. So now we want to go and put it into arrange it according to our trend. So we want increasing, which means we'll start with the smaller ones. So the ones with fewer layers here are going to be the smallest, so sodium and fluorine. And then between sodium and fluorine, which one is going to be smaller of those two? Well, it's going to be the one with more protons, right? The more attraction in the nucleus. So sodium is going to be our smallest one here, and then the fluorine is going to follow. And then between these two are both much larger because it has another layer of electrons. But calcium has more protons, so it's going to be smaller than the sulfur. There you go. Hope that helped. Alrighty, our next trend here is ionization energy. Ionization energy is the amount of energy, surprise, surprise, needed to remove the first electron from an atom. So kind of think of atoms and the electrons and protons in an atom as being kind of like magnets that are held together by their opposite charge. And if you want to
pull off one of those electrons, you're going to have to use energy to do that. The trend is the opposite to that of radius. So if you know the radius trend, you just it'll be the opposite for ionization energy. So if the radius decreased going to the right on the periodic table, the ionization energy will decrease going to the left. And if the radius increased going down a group, then the ionization energy will increase going up a group. So they're opposites to each other because the smaller the radius, the harder it is going to be to pull off that first electron. Now, of course, most atoms have more than one electron, and so you can have multiple ionization energies, which means as more energy is added, you can get more electrons to come off of an element. Now, there's a pattern that this follows as well, which is kind of neat once you recognize it. And first off is that as soon as you remove an electron, the remaining atom then becomes positively charged, right? Because now there's an imbalance. There's more protons than there are electrons. As soon as you remove one, it's a positively charged ion. And that makes it harder to take off the next one because the whole thing's positively charged and electrons, of course, are negative, and it makes it more difficult or require more energy to pull off that next one. And then the next one here is going to be even harder. It's going to require even more energy to pull that one off. And so they're all going to increase as the charge of the whole ion gets bigger and bigger. And then there's a big jump. Once we pull off all the valence electrons, we got to go down to another layer that's closer to the nucleus. And when it's close to the nucleus, that means it's going to have a much bigger increase in the amount of ionization energy required to take off that next one. So you see a big jump in the ionization energy when you get to a new layer of electrons. All right, so what does this look like? Well, you can have a table of ionization energies, and even without the elements, you can determine which group an atom is in if you have its ionization energy. So you can see the first ionization energy here required 495, let's say, joules to pull off that electron. And then the next one, a whole lot more. It's about 10 times as much energy needed to pull off that next electron. That's because it's sodium, and you know sodium only has one valence electron. So once that valence electron is pulled off, the next one requires a lot more energy to do so, and you see it goes up from there as the ion becomes more positively charged. The magnesium has two valence electrons, so you have a first one that comes off, second one that comes off takes a little more energy, and then there's a big jump. So big jump in energy because you go to the next layer of electrons that went down. So again, and the big, was that 5 times as much to get to the next electron coming off. Aluminum has 3 valence electrons, so you got easy, 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 hard, right? So this is where the big jump is. And then silicon has 4 valence electrons, so it's going to be easy, 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 hard. And so there's that same pattern too. So you can use these values of ionization energy to make predictions about which group an element is in and help you understand the way in which the atom is structured. Okay, another couple of trends that also follow the exact same pattern as ionization energy is electron affinity. So electron affinity is the amount of energy given off when an electron is added. So basically the opposite of ionization energy, but it follows the exact same trend. If it requires a lot of energy to get an electron to come off, it's going to give off a lot of energy when that electron is added. And the other one is electronegativity. That is the amount of attraction for shared electrons when there's a bond. So we're going to use that a lot more later when we start looking at bonds. So electronegativity and electron affinity both follow the same trend as ionization energy. Basically, they increase as you go across a period, and they decrease as you go down a group. Okay, so our last trend we're going to look at here is reactivity. Reactivity is related to the other trends we've already done. It just depends how the elements react. So we'll start with the nonmetals. Our most reactive nonmetal is fluorine, and that's because it has the highest electron affinity. And all your nonmetals are going to react by gaining electrons, and so the more electron affinity they have, the faster they will react. So reactivity increases towards upwards on the periodic table, and it also increases going to the right, which makes fluorine the most reactive since all your noble gases don't react at all. So reactivity increases up and to the right if you're a nonmetal. If you're a metal, then it's the opposite because metals are going to react by losing their electrons, and so the other F on the periodic table is francium. It's going to be your most reactive metal because it has the least attraction for that valence electron, and so gives it away very easily, and so it is the most reactive that way. So reactivity increases as you go down and to the left for the metals, and it increases as you go up and to the right for your nonmetals. Great, okay, talk to you soon.